Hi grade 11s, good to be back with you again. Learn Extra, Physical Sciences, and today we're going to be looking at electrostatics. Now electrostatics is an amazing topic and there are many interesting ideas that we're going to look at. So stay tuned and make sure you've got the basics right, because if you get the basics right, you'll be able to solve even the most difficult problem that you will come across. The important thing to note is that sometimes many of the questions that we cover in grade 11 are actually asked in the grade 12 exam. So pay attention, make sure you've got it sorted out. Here's an overview of what we're going to be looking at today. We're going to do some revision about what electrostatics is, different types of charges that you've got, the idea of the conservation of charge, Coulomb's law, very important law that explains some sort of reasoning about the attraction between charges. Then we'll talk about electric fields, the properties of those electric fields, and the idea of electric field strength. We'll move on to talk about electrical potential energy and potential difference. So that's the overview of what we've got to do. Now there's a lot to cover, so let's get into it straight away. And the first thing is, well, what do you know about electrostatics? Well, first of all, you should know that it's different to current electricity. Electrostatics is the stuff that occurs on the surface of insulators. So how do we charge something and make it electrostatically charged? Well, you've probably experienced it. If you're walking along a carpet and you rub your feet on the carpet, you apply some friction to the bottom of your feet, and then you go and touch somebody, sometimes you feel a little bit of a shock. The other thing that's quite common is if you take a ruler like this and you rub it with a cloth, then what we can find is that after a while, this ruler becomes charged. The cloth also becomes charged, and we can show that charge by putting it against something that might not be charged, for example, little pieces of paper. And if we do that, sometimes what happens is we get the pieces of paper sticking to the charged object. So that's an example. If we take a rod like this, glass rod or a PVC rod, Perspex rod, rub it with a piece of cloth, even a piece of woolen jersey, you'll find that you can do all sorts of things. You can get water to bend. You can get dust to settle on a screen. These are the ideas of electrostatics. So you might be wondering what electrostatics is about. It's really important. So pay attention and let's get going with that particular topic. So the first thing that we need to talk about is this idea of charge. So when we think about charge, we might be thinking about the atom, and that's a very good place to start. We know that matter is made up of atoms, which then go into either making molecules or structures that are bigger, giant molecules or ionic substances even. So these substances, right at the bottom, the atom, has positively charged particles called protons and negatively charged particles called electrons. And we know that the one is positive and the other is negative. Well, we've just given them those words. What we know is they're opposite in nature. So that's where we're going to start. We say there are two types of charges. Those that are called positive, when a substance has lost electrons, and you do that by rubbing, by friction. Or when something is negatively charged, it's the opposite charge, then it's negatively when the substance has gained electrons. So you can take a cloth and a rod, and you will either transfer electrons from the cloth to the rod or from the rod to the cloth. The thing is, overall, the total number of charges remains the same. And that's an important principle that's known as the law of conservation of charge, which is the very next thing that we're going to talk about. Conservation of charge. The law of conservation of charge states that the charges cannot be created or destroyed, but are merely transferred from one object to another. the amount of charge in a closed system remains the same. And I would go as far as saying the amount of charge in the universe remains the same. Number of protons equals the number of electrons. And so we do know that there are nuclear reactions as well, and they're producing all sorts of strange particles, but for every positive particle, there's a negative particle. And so this principle of conservation of charge is really important. How do the charges interact with each other? Now, that's a very important idea, and we're going to just draw some pictures here. Something that you should remember is that what we would say is that like charges, what do? They will repel. There will be a force of repulsion. So they will repel each other. But unlike charges, so if we have a positive charge and another positively charged object, what do we know is going to happen? Well, they're going to, if they're able to move, they're going to be pushed away from each other. If we similarly had negative charge object, a negatively charged object and another negatively charged object, they are both the same type of charge. The negative and the negative, what's going to happen to them? They're going to repel. They're going to be pushed away. So there are forces of repulsion. But what happens if we've got a negative charge and a positive charge? Well, here, these are unlike charges. They're unlike. They're not the same. Unlike means not the same. Unlike charges. And what do? They attract. There's a force of attraction. Okay. So these are two very important principles. It also applies to magnetic poles. So we know that a north pole will repel a north pole, a south pole will repel a south pole, but a north pole will attract a south pole. So be aware of that very important principle. But can we calculate the force of attraction or the force of repulsion? Well, fortunately, there was somebody that did a whole lot of experimental work, came up with a law. His name was Coulomb. He's a French physicist, and we honor him by giving him the unit of charge. The symbol for the unit of charge is a C, and we measure charge in coulombs. Coulomb's law states the following. It says, the force of attraction or repulsion, so when we're dealing with attraction or repulsion between two electrical charges at rest, is directly proportional. Very important relationship and important for us to understand. The product. That means you've got to multiply them together. The product of the charges, okay, and inversely proportional. So here's an important idea. Inversely proportional to the square, that means you must multiply it by itself, of the distance between them. And there's the expression in mathematical terms. We say F, the force of attraction or repulsion, is equal to K. It's written as an equation because we've taken away the proportionality. There's a constant involved. That constant we'll talk about is Coulomb's constant. Q1, Q2 over R squared. So Q is the charge. The unit of charge is measured in coulombs. So be aware of that. The symbol for charge is Q, and in this case we're using a capital Q, and the unit for charge is Coulomb, and it has a capital C. Don't try and mix those up. Remember the difference between unit and symbol. The symbol can stand on its own. The unit must always have a number with it. So we would say 9 coulombs. It has a 9 in front of it. That's how we can work with it. Be aware of that. Then R is the distance between the charges, and we should be more explicit with that and say it's the distance between the centers of the charges. So where the charges are, we want to get that exact distance. So, and it's measured in meters. Coulomb's constant, this K value here, is a value of 9 times 10 to the 9 Newton times a meter squared times coulombs to the minus 2. So that's per coulomb per coulomb. Okay? Hope you've got that idea right, and that's Coulomb's constant. Now we're going to use this equation quite often in solving electrostatic problems. The important thing to notice here is that you've got to work in SI units. Now, 1 Coulomb of charge is huge. It's absolutely massive. There are billions of little charges sitting on 1 Coulomb. So we often have to work with smaller units. And here is where the SI unit or the SI system of measurement, the metric system, becomes quite useful because we can very easily make a unit smaller. And that's what I want to show you right here. So what we need to recognize is that we can start off with 1 Coulomb. And we can say, yeah, we've got 1 Coulomb, and that's fine. But if we had a smaller unit, let's say 1,000th of a Coulomb, so that's 1 times 10 to the minus 3 coulombs. Then what we would say that is, we don't want to keep on writing it like that, although we like using scientific notation. Is there a shorthand way of doing that? And say, yeah, of course there is. We say that's 1 millicoulomb. 1 millicoulomb. And then if we wanted to get 1,000 times smaller than that, we'd divide by 1,000, and we'd get 1 times 10 to the minus 6 coulombs. Now, we're getting into the region where we can use this value. It's quite common for us to get this type of Coulomb. It's 1,000,000th of a Coulomb. Very, very, it's still quite a large charge. We write it as 1 microcoulomb. So this is micro, and this was milli. Okay? And we can go even smaller. We can say, what about 1 times 10 to the minus 9 coulombs? Well, that's equal to 1 nanocoulomb. Now, you might have heard of nanotechnology. It's at this level. It's at 1,000 million of a coulomb. Very, very small. 1 times 10 to the minus 9. And so we call this nanocoulomb. And then the last one, which isn't the smallest by any means, but we can get down to 1 times 10 to the minus 12 coulombs, and that is called 1 picocoulomb. Picocoulomb. Now, you are going to need to make sure that you know how to convert, and it's really easy. Notice how I've set it up for you. If you remember that pico is times 10 to the minus 12, all we've got to do, instead of writing the p there, instead of writing that p, when you're given it, just replace the p with times 10 to the minus 12. Instead of writing the nano for the n for nano, write times 10 to the minus 9. And instead of writing the u for micro, write times 10 to the minus 6. If you've got that in your head, you've got that conversion factor, you'll be A for away. You'll get 100% on doing your conversions. So now let's have a look at the next concept, which is a really important one. It's the concept of an electric field. And when we talk about electrostatics, we need to understand what an electric field is. So if, for example, this was a piece of paper and it was isolated, so suspended or held separately, nice piece of paper that's able to carry some charge, then what we would recognize, it affects the environment all around it, in a region of space around it. It's not just flat, but all around it. Anything else that is charged, that was brought close to this charged object, would experience either a force of attraction or repulsion, because this region of space around a charged object is known as the electric field. So let's look at the definition, and you can see if what I've said makes sense to you. What we're going to say is this. An electric field is a region, very important. It's in 3 dimensions. It's a region in space in which an electric charge will experience a force. So we could have this region that's this electric field that's generated by a charge. Another charge coming in will experience a force of repulsion. If we put an insulated, neutral piece of substance in there, it might not experience a force. It might be polarized to become charged and might then experience a force, depending on how large the force is. But I like to think about it this way. I like to think that if I've got a large charge, let's call it a positive charge for the moment, And I think about this as the one that's generating the field. I like to think about this as the mother charge. Okay? And it produces an electric field, so a region in space around it. If I want to bring a little baby charge into this space, and it's a little test charge, also positive, then I can ask myself the question, what sort of force will this one experience? If it experiences a large force, then I can say the field is very large. So this is your baby charge. This is your baby or test charge. Okay, and we're testing the field, a region of space. We can put it at different distances, different positions, and we can get a pattern of what this electric field is around the mother charge. The mother charge is generating the field. Now, of course, the baby charge is also generating a field. It's a smaller field, but it's still generating a field. And so we need to understand that every charged object has this region of space around it. It's very similar to the idea of a gravitational field. Around every object that has mass, there's a region in space that carries on and on and on, that another object, if it has mass, another substance has mass, enters that field, it will experience a force of attraction. So bear in mind, this is not just about electrostatic fields. The concept of a field is applied to gravitational fields and also magnetic fields. A magnet, bar magnet, we bring another bar magnet or a magnetic material into that region of space, it will experience a force. And that's what the idea of a force field is about. Now, we can't see the force field. A force field, the electric field, is invisible. Can't see it. So how are we going to represent it? And that's what we want to just find a little bit about. We can't see it, but we can represent it. It's not visible, but the direction, we'll look at it as the direction in which a charge, a positive charge experiences a force can be used to indicate the pattern. So when we have a positive charge and we place that baby charge, that test charge into the field, and we see that it moves to the right, then we're going to say that's the direction of the field. So we can draw that and we can represent it by using some simple rules, which we will call the rules or the properties of field lines. So around a charge, we can draw some pictures to represent how strong and how weak an electric field is. Let's just go over the rules for drawing fields, because you can be asked to draw them. So we draw them with these lines, which are known as field lines. Field lines are in the direction indicated by the movement of a small positive charge, which is the baby or the test charge. The field lines can never cross. Areas where the field lines are close together indicate a strong field, and where it's weak, they're further apart. So bear that in mind. Field lines begin and end at right angles to the charge. This is a very important idea. The word perpendicular means at right angles, and when you've got it on the charge, you must make sure that you try and draw it properly like that. Also bear in mind that field lines are continuous. There's no break in them. They carry on. And field lines are three-dimensional. It's because we're talking about a region in space. I've tried to illustrate that to you by using my hands to say around this charge. It's up, down, to the side, below. It's not just a flat picture. When we draw the field line diagrams, we're going to draw a flat picture, but notice that it's actually in 3 dimensions. So what do they look like and what can we show? Let's go and have a look at a simple field line diagram. And we're going to start with just drawing, let's draw one, and I'm going to do this with my pen rather than with that fancy tool. I'm going to draw a circular charge like that. Let's call it positive. Now, what I want you to think about is we're going to do some tests here, and we're going to say, what if? What if I put a little positive charge at that position over there? What sort of thing would you expect? That tiny little charge, this big charge, tiny test charge is entering the mother or the field of this big charge, what's going to happen? Well, clearly they're both positive. There's going to be repulsion. If this one is stationary and it's fixed in position, the test charge we can think as being able to move, then what we're going to say is, well, we think that there should be a field line that is indicated at 90 degrees to that surface, and it carries on like that. So the direction of that field would be outwards. That positive charge is going to be repelled, and it's going to be repelled outwards. If we recognize that that charge was placed at another position on that line over here, it's still going to be moving in that direction. So we could plot a whole lot of points. Similarly, we could draw some more lines. I'm just going to draw a couple in. Not going to complete the diagram. You're going to see some drawings, and you see some drawings in your notes of completed field line patterns. Just draw a couple in and make some notes here. We can see that these ones carry on. Notice they don't cross. They start on the surface. When it's circular, it's quite difficult to get the 90 degree to the surface in, but they are more or less at 90 degrees. We need to indicate the direction of those field lines, so we're going to put the arrows on indicating that they're outwards. So there's the field line pattern for a positive charge. What I want you to notice is if you look at that picture, and we're going to examine it in a little bit more detail, the closer you are to the center, to the actual charge, the closer the field lines are. You get further apart, these field lines get further apart. Look here, let me illustrate it for you. So if we take a look at the distance between this, just draw a box for the moment, and notice that box contains those two lines. If I now take that box and I move it, I'm going to pick that box up and I'm going to move it over here. Notice that field line's not crossing it anymore. There's only one field line going through it. So over here we would say this field is weak because it's further away. This field over here, where I had it earlier, because it was able to cover two field lines, we would say is stronger. Makes sense. It's strong. So what we've got is a radial field. This type of field is known as a non-uniform sorry, I've spelt that incorrectly. Let me just rewrite it. Non-uniform field. It's changing every time you move away. Now, that shouldn't be too much of a surprise, because we looked at Coulomb's law and we said, well, the further you go away, there's an inverse relation to the distance between those substances, between those charges. The further you go away, the weaker the field's going to get. It's 1 over r squared. Very quickly, the field gets weaker the further you get away from each other. So bear that in mind and take a note of that picture. What about a negative field? Well, it will also be a non-uniform field. So if we had to draw a negative field, we ask the same question. In which direction would a little positive charge test charge move? If it was free to move, in which way would it go? Well, I don't think it's difficult to see that if we had a positive test charge, instead of being repelled, this one is now going to be attracted. So around a negative charge, we get a field line pattern that looks something like this. And all the field lines are moving towards the negative, because it's showing you that a positive test charge would be attracted to that big charge over there. So there we go. Make sure the lines don't cross. Notice again, close to the charge, they're close together, further away. So that's why we say this is also an example of a non-uniform field. Now, what happens when we bring two positives together, two negatives together, or even a positive and a negative together? Remember, we said that we'll expect a attraction when they're oppositely charged, when they're not like, but there will be repulsion when they are like charges. So have a look at the diagrams and let's see if we can make some sense of them here. So here we go. Notice here is a positive charge. The field lines are going out, and what we've got here is the field line has just been cut off. It's gone up over there. Just draw it in. The one down here has been cut off as well. Needs to be continuous. And what we're seeing is the field lines are pulling towards each other. So in this way, we can see that there is an attraction. This is what represents attraction. So we'll notice when we get a field line pattern like this, we get attraction. Attraction between the oppositely charged substances. But notice when they're the same charge, both positive, then they're repelling. They're pushing against each other. So this one wants to push down this way, that one wants to push that way. Over here, we get a region where the two forces are acting on each other. This one is pushing that way. So this is charge, let's call it charge A, and that one's charge B. And so at this point, there's actually no field, because the magnitude of the force in that direction and the magnitude of the force in that direction, they're equal. So they cancel each other out. And a little test charge placed over there would not experience any field. So we would say the field strength over there, or the force on the test charge, is going to be 0. Similarly here, notice the field line pattern around two negatively charged objects. The field line pattern now is inwards, but there's also this region of space here where the fields are not going to experience a force. A little positive charge here is going to be pulled this way and that way, so there is a resultant of 0 force on that charge at that very particular point. Okay, so there are some field line patterns with set charges, charges that are circular. These ones can be balls that have been painted, pith balls, polystyrene balls. They've been painted with some metallic paint, and they can collect charge on their surface. They might have been rubbed, they might have been charged in some way. So they're usually isolated, sometimes on a stand, sometimes hanging from a string. We say that those are all non-uniform, but there is an example of a particular type of field that is not non-uniform. In other words, it's uniform. What does that mean? Well, it means that it's constant. The field doesn't change. And this occurs when we have two charged plates. So I want us to look at two parallel plates here. And we connect these plates to a battery. And it's the crossover between electrostatics and circuits. What we have here is a positively charged plate and a negatively charged plate. And what I want you to see is that these lines are all equidistant. So if I draw a box again, like I did previously, and that box covered those two field lines, and I position this box further down, see, it still covers the two field lines. And even over there, it covers two field lines. And over there, it covers two. Wherever I choose to put it, as long as I've got one field line in, I'll have the other field line in. It's very difficult to just get one field line. Over there, there's one example, but it has the area to cover two field lines if I keep the position about the same. Even over there, it's got a little bit weaker, but over here, these are parallel to each other. This is a uniform field. It is uniform. That means it is constant. It's the same everywhere, okay? Which means that a charge placed in this position is going to experience the same force as if it was placed in that position or in that position. It will experience the same force throughout this area, this region of space called the electric field. Notice at the end, these lines aren't parallel. The field's been distorted, but it's important to note this is still drawn at 90 degrees, and it ends at 90 degrees over there. Okay, so the concept of a uniform field is really very important. And we're going to do some calculations with those a little later and make sure that you've got the understanding of what's happening in a uniform field. We will also look in a different lesson at capacitors, where we have two oppositely charged plates. And this is where parallel plates and the field between parallel plates is very important. It's an application that we use almost every day. Right. Now, having talked about electric fields for quite a bit, we've seen what they look like. The question is, how do we know how strong they are? So we're going to go and investigate the idea of electric field strength. Let's go and have a look at the definition. We say the electric field strength is the force per unit charge. Now, very important. Force per, which a positive charge will experience at that point. So let's try and wind back a little. So if we've got mother charge over here, and we put a test charge over here, that's the test charge, we're going to say the electric field strength, E, is the force that this thing experiences divided by the little charge, the test charge. And there we've got it written down nice and bold. Please bear in mind that this is the test charge. So it's the force experienced by 1 coulomb of charge in an electric field. So we need to understand that this is the idea of electric field strength. The important thing that electric field strength is a vector, so it has direction. That's why we made such a fuss of the field lines, because we could see they had a direction, a particular direction in which to go. So what we would recognize is that we need to work out the magnitude as well as the direction. And so often we have to say in which direction something's moving. We would say either towards or away. It's either being attraction or repulsion, and we need to be giving that as an answer. So what you need to recognize as well is that you can use this formula to calculate the magnitude of the force. We can take the electric field strength, if we're given it, and we multiply it by the value of Q, the charge placed at that position, and we can always work out the force of repulsion or attraction. Now, that's not the only way of working out electric field strength. That's the one definition of electric field strength, and we're going to go and have a look at a second idea of electric field strength, which says, okay, so let's have a look at this. We've said electric field strength is equal to the force divided by the test charge. Okay, so if we had over here two charges, and one I'm going to call A, and the one I'm going to call test, okay? Then what we also know is that if we take Coulomb's law, we can say, yeah, well, we can work out what the force is. The force is K, Q of A, times Q of the test, divided by R squared. But hold on. If I take that F and I substitute into this equation here, so take all of that and just replace F, and wherever I see F, I'm going to put that ugly expression, then look what happens. Really something quite beautiful. We're going to get K, Q, now I'm going to do it exactly the same, A, Q, test, over R squared, and then over this thing over here, which was Q test. Now, you should know that what the rule is that you're going to divide, and that's over 1, so you tip and times, and what does that work out to? So if you're dividing by a fraction, and we say this is test over 1, then we're going to multiply by 1 over Q, and I think you should be able to see, without too much exertion, then what we were going to get is this is going to be K, QA, Q test, over R squared, divided by, also that R squared multiplied by Q test. And what do you think we should do? Well, Let's cancel those out. Simplify the equation. So that gives us an expression for E. So we'll be able to say that E is equal to the electric field strength, and this is the electric field strength produced. That's the one that is being made. If you look back over here, we wanted to know the electric field strength at that point. Well, we still want to know at that point, but what have we got? We've got the mother. We've got the one that's making it. This is the producer. Okay? And this is the distance between them. There's R. That's the distance between them. So if we know the mother charge, then we can calculate the electric field strength at any position away from that mother charge. Please be aware that those two equations are different. You're using different Q's. In the one, it's the one that is producing the charge. The other, we're using the effect of the charge. We're using the test charge to divide by. But they're two ends of the same spectrum. We use these two equations. We can use them for all types of fields. This one we're using for when the field is non-uniform. Okay? Please bear in mind that we would use that because of Coulomb's law in a non-uniform field. So what happens in a uniform field? Well, let's have a look. There is a slightly different equation that we can use, and that equation will require some additional formula, which we're going to come to as we define our next concepts. And that concept is the concept of electrical potential energy and potential difference. So when we're dealing with parallel plates, the formula is a little different, and we're going to look at that after this explanation. So let's go straight on to electric potential, energy, and potential difference. Let's have a look at our non-uniform situation here. We've got position A and position B. There is our positively charged sphere, and what we're going to say to ourselves is, if we want to, can we work out how much electrical energy, what's this idea of electrical energy all about? Like we have gravitational potential energy. We have a gravitational field and we have gravitational potential energy. We know that if you do work against the gravitational field, then what happens is the object gains gravitational potential energy. Well, exactly the same thing happens here. If I take A at this position and I move it closer, what am I doing? If A is a positive test charge, I'm going to do work on it. I've got to do some work. The field, the force is pushing against me, and remember, work is equal to a force times the change in position, and we could even put in a formula over there. We'll come to that in a short while. Work is being done against this thing if I move it. So what we recognize is as I do work, it gains energy. So if I take it from very far away, from infinity, and I do work on it to get to a position in the field, then it has a certain amount of potential energy. Notice that this one, A, is closer than B. So what we would say is A is at a high potential. It has potentially more work was done to bring it from far away. It's at a high potential, and this one is at a low potential, because it's further away. Notice the distance is much longer between these two. Look at that radial distance there compared to that. So to get this one to the same position, I've got to do more work on it to get it closer. So we'd say that's at a low potential, that's at a high potential. Notice if I have to do work against the field, I gain electrical potential energy. Now, there is a symbol for this. We say that U is the symbol for electrical potential. And we define U in a strange way, but it's simply this. We say it's K Q1 Q2 over R, not over R squared. And the reason for that is because you are doing work on it. It's the force times the distance that you've got to move it. And so it's not that strange when you think about it. It's the energy gained when you're doing work against the field. So what happens if I take a positive charge and I move it in that direction? Well, then I'm working with the field. In fact, the field is almost doing work on the charge, and we're saying we're losing potential energy. So gaining potential energy is when you're going against the field. Losing potential energy is when you're going with the field. It's all defined, though, in terms of a positive field. So positive charge, positive field, and we define it like that. Now, this is quite clumsy. Really is quite clumsy. So people wanted a better way of doing this. And they said, how can we simplify it? And so they said, let's try and measure the work, and let's try and measure the distance between where that work is being done. So we don't just want an ideal potential where something's come from a very far away and at a particular point. We're going to look at 2 points. And we're going to say when an object moves from A to B, it's going to either lose or gain potential. And we would like to know what the difference in potential is. If you've got a difference, then you're going to need 2 points. So they defined it in terms of this. They said what we're looking at is potential difference. The definition of potential difference, we can't just be moving any old charge, so we'll need to use a particular charge. Obviously, if you use a small charge or a big charge, the different amount of potential energy, different amount of work is required. Potential difference is given a symbol V, and we'd say V is equal to W divided by Q, where Q is the charge that is being moved. It's like the test charge. So how much work is being done per unit charge in moving from A to B in some other electric field? That is the formula that we're going to use, and the same formula will apply in circuits. So we will use the same potential difference formula in circuits. Okay, just want to make sure that you've covered it and make sure that we've done that in terms of non-uniform fields. But now what about uniform fields? Let's have a look at that idea of 2 parallel plates again. So here we go. We've got a charge between 2 parallel plates. This is the positive plate, and that's the negative plate. And we've got this charge over there. Now, you wouldn't take much to recognize that there is a force that's acting on this charge, and that force is going to be moving in that direction. What we also recognize is that if it moves in that direction, it's going with the field. So it is losing potential. So this is moving in that direction. It will be losing electrical potential. Often what happens is that, in fact, this force is going to cause these little charges, can be little droplets of oil or little droplets of air even, little air molecules. They can even accelerate. Work is done on them. There's a force exerted, so there is work in moving it from this position. Remember what work is? It's the force, work, force, times the change in position. So if it moves from there to there, the field is doing work on the charge and it's losing electrical potential. When it does it against the charge, here it would be gaining electrical potential. So let's just try and put all of this together in some sort of equation, and we'll see what we've got. We recognize that we said that V is equal to W over Q. So if I'm wanting to get W in another way, Okay, I'm wanting to rewrite W. Then I'm going to say W is equal to V times Q. Now, W is also equal to F times delta X. So here we go, and we can say we've got that so far. Now, if I recognize that something is going to move from the positive plate to the negative plate, then that's the distance. Then delta X is equal to the distance between those plates. So what we've got here is instead of saying delta X, which could be any old distance, I'm going to substitute D in. And here is my next step. I'm going to recognize that force is also equal to, do you remember what it was? We defined it earlier. We said the force could be defined by the E times the Q value. So what I'm going to do now is I'm going to substitute that, because remember, E is equal to F over Q, so that's right. So I'm going to substitute EQ, and I'm going to say EQ and D is equal to VQ, which is also equal to W. So there we've got a whole string of equations that are quite nice to use. One of the things that comes out of this is that I can take these two, which is my expression that I'm looking for, and I'm going to say E times D is equal to V. Another way of expressing that is to say that E is equal to V divided by D. And that becomes, remember we spoke about it, the electric field strength between parallel plates. We didn't have the formula because we didn't have the definition of potential difference. But here's the third way of defining electric field strength. When you've got a uniform field, what we can say is that it is the potential difference between these plates. So if we know that there's a battery, that there's a potential difference it created to make this a positive and that a negative, and we know the distance, then we know what the E value is. E is equal to V over D. Now, the conclusion of that is that we've got two formula. This one, E is equal to F over Q, and we had electric field strength. The units here would be 1 Newton divided by a Coulomb. So it's 1 Newton per Coulomb. But if we looked over here, we would see that it's 1 volt per meter. The interesting thing is that these two are identical. That's exactly the same as that. We say they're exactly the same. So 1 volt per meter or 1 Newton per Coulomb is the unit, the SI unit for electric field strength. Okay, I think we've more or less wrapped up the idea of potential difference, work done, and we're going to now go on and do some examples. So let's go to that first example right away. Question 1. The values in the following table were obtained during an investigation relating to Coulomb's law. And so we had a number of experiments, 1 to 7. The electrostatic force was calculated. The charge Q1 is given in times 10 to the minus 5. Charge Q times 10 to the minus 5. The distances were given, and then there's some space for us to fill in some things about r squared and 1 over r squared. Right, let's have a look at that table, and let's see what the questions say. First question says, identify the independent, dependent, independent, dependent, and constant variables for experiment 1, 2, and 3. So we only worried about 1, 2, and 3. So it's only that data that we need to look at. And we're going to need to identify what is independent, what is dependent, and what is constant. This is all about the skill. Remember, the things that you are changing is the independent variable. The thing that is dependent on that, the outcome of that, is going to be the dependent variable, and the things that we keep the same are going to be the constant variable. So let's have a look at the data and let's see what's happening. So notice here, first of all, very easy to see that those charges are all kept the same. So there's no change in the charges. So it's perhaps easiest to say, what's the constant? The constant is charge. Q1 and Q2. They're kept constant. Second thing to look at is, what do we do? Well, you see, it's difficult for us to change the force. We've got to do something to make the force change. So the force is the output. It's the dependent variable. Whereas the thing that we are changing, if we look here, it's a change in distance. We can easily move the charges from 1 meter to 2 meter to 3 meter. So I'm going to tell you, or say, that the independent variable, independent, is the distance between the charges. And the dependent, the one that is the output, is going to be the force. Force of repulsion, the electrostatic force. We're not told whether that's positive or negative, but it is an electrostatic force. Which experiments show that the relationship between force and charge Q1? Now, this is very important to take note of. We're wanting force. Force is the dependent variable. So we want to look at where Q1 has been changed and everything else has stayed the same. Have a look. We want Q1 to change, or have something where Q1 is different and everything else is the same. So Q1 over here, that one, Q2 has changed. Notice here there are 3 meters. So we're wanting something where there's a constant, there is a difference in Q1, but a constant in all the others. So look here, that one, and that one, and that one. Q1 has changed. It has increased. I hope you can see that. So there's a change in Q1, but look, what's being kept the same? Q2 is kept the same, and the distance is kept the same. So if we identify that, we must say that it's experiments 5, 6, and 7 are going to be the ones that are going to be showing you the relationship between force and charge. So let's write it down as we would. We would say experiments 5, or is it 5? 5, 6, and 7, yes, 5, 6, 7. And what we're going to say here is that Q1 is the independent variable, changes, and it's the only thing that changes. Q2 and distance are constant, and the force is the dependent variable. So there's a fair test. We can make a dependent variable. So we can do a fair test because we've selected our variables appropriately. So recognize that, and you've got the idea that this is what you're comparing. You're comparing the relationship, you're investigating the relationship between the independent and the dependent variable. So your hypothesis for this, your investigative question, could be something like, what will happen if I increase the charge on Q1 to the electrostatic force? So bear that in mind, and you can see that it's only those ones that are applying. Okay, let's move on to question 1.3, and it tells us here that we need to redraw the table and complete the table for experiments 1, 2, and 3, and then to do a sketch. Now, I know I put that on the next page, so let's go and fill that in over there so that we've got it all clear for us to fill in. So what we need to do is to identify what r squared is. There's the distance, that's r. So let's take it. We want r squared. Well, 1 squared is 1, and 1 over 1 is 1. So there's no change there. Whereas 2 squared is going to be, that's right, 4, and 1 over 4 is a quarter. And the next one, we're dealing with 3. Let's go to experiment 3 over here. And we're going to say, when we square that, we get 9. And we're going to say that is 1 over 9. You could use your calculator to show what the decimal value is, and the decimal value is not difficult to work out. Let's just do it over here. We're going to say, use the function over here, 1 over 9 equals, and if we convert that, 0,111 recurring, so you've got the decimal number as well. You could fill that in. It wouldn't be wrong to use decimals, but it's also not wrong to use that value of 1 over 9. Okay, well, the next part of that question was we were asked to draw the graph, to show the relationship. Now, those numbers are not very pleasant. We've got 1, 0, 0,01, 0, that's 0,25, and 1. Now, we've got to plot that against the force. So first of all, let's just decide how we're going to do it. Draw a sketch graph, so we don't need to plot it accurately, to show the force against the distance. And I just noticed that that's against 1 over r squared it was supposed to be. 1 over r squared, it's in your notes like that, so how are we going to do that? So we've got those values. Notice it's a sketch graph. So as I said earlier, we don't need to be that worried about getting a grid up, but I'm going to try and put it in as nicely as possible. So let's get going. We're going to put 1 over r squared as the thing that we're changing, and we're going to put the force over here. Now, it's a sketch graph. So let's have a look at the trend. What's happening in this case? Look at the force here. The force, when this is the smallest, 0,11, then this is 2,5. When it's 0,25, it gets bigger. When it is 22,5, it gets to 1. So what I'm seeing is that as this one increases, so does that value increase. You can see that. So we would start by plotting that up. And if we looked at Coulomb's law, we would recognize that F is directly proportional to 1 over r squared. This whole value, excluding the denominator, that whole value, they're directly proportional. So if this one increases, that value is increasing, then that value is increasing. That's what we're seeing from the graph. And so therefore, we would recognize that what you're likely to get, if you plot this out, and we were just asked to sketch it, so we can put it in a straight line, because we know that this is true. So we can say, yeah, we know that this is true. So force is directly proportional to 1 over r squared. We're going to get a straight line passing through the origin, and perhaps we just need to put one value in. So we would have one value from there just to show it. We'd take 1 and 22,5. So somewhere over here, we're going to say, let's put onto our graph, just to show that's 22,5. And the value for 1 over r squared at that point is 1. And that will give us a nice sketch graph in terms of having the axes. We should really say force in newtons and 1 over r squared in units of per meter to the minus 2. It's it's per meter squared. Okay, per meter squared. So we've got that. What does the graph tell us? So let's go to that and make sure, give the relationship in 1.4. Well, we've said it already. The force is directly proportional to 1 over r squared. Okay, so that was quite clear from that graph. Right, now we get into some calculation work, and here's the question. We're told this, that two charges plus 5 nanocoulombs and minus 15 nanocoulombs respectively are placed 5 millimeters apart. Calculate the electrostatic force between the charges. Now, we recognize the one is positive and the other is negative. We must bear that in mind, that this is going to be a force of attraction. We'll put that in the answer. So we've worked that out right from the beginning. The next thing, that when you're given one of these problems, you identify, you're asking for the electrostatic force, you're going to use Coulomb's law. So the force of attraction is going to be K Q1 Q2 over R squared. And that's not too difficult, but what we need to remember is SI units. So what are our conversions that we're going to do? Q1 is going to be 5 times 10 to the minus 9 coulombs. I've just converted. That's nanocoulombs. This one was minus 15, so Q2 is 15 times 10 to the minus 9 coulombs. Then the last thing that we need, the distance between them, R value, was given as 5 millimeters, so we're going to say 5 times 10 to the minus 3 meters. You see, that conversion system works. So convert to SI units. Convert to SI units. And we've done it. We've got it right. We've identified that. Now it's just a case of substitution. So let's go and substitute these values into our Coulomb's law, and we can do some calculation. So write it out, Q1, Q2, K over R squared, K Q1, Q2 over R squared, and we're going to substitute in 9 times 10 to the 9 times, this one was 5 times 10 to the minus 9, and this next one was 15 times 10 to the minus 9, all divided by, and here is where lots of people make a mistake. They think they've got it right, 5 times 10 to the minus 3, and they're very happy, and they might even write a 2 over there and they forget to do it. Please don't forget to do it. Make sure you include the squaring in your calculator step. So let's go and make sure that we follow that through, and we're going to say 9 exponent 9 times 5 exponent negative 9 times 15 times 10 to the negative 9. Okay, I like to say that's the numerator. You can even push equals at that point. You don't have to. Divided by, I like to put this in brackets, 5 exponent, again you don't have to put it in brackets, minus 3, minus 3, and then I want to square that whole thing. So I'm going to close the bracket, and I'm going to say I want that squared, and then I push the equal sign to get my answer, and the answer comes out as equal to 0,027. So I'm going to write that down, 0,027. Just extend the page, 0,027. Now, you might have noticed that I didn't put a negative in here. If I had, the answer would have been negative, but I put that right at the top there because I recognized that it's plus and minus. In my answer, I must recognize that this is newtons and that it is attraction. I can simplify this one step further because normally you have to give the answer to 2 decimal places. So what we might even be able to say is that it's 0,03 newtons attraction. That's not critical if you leave it like that, unless this question specifically says 2 decimal places. That's what your answer would be. Okay, I think we've got that one in the bag. Let's move on to the next question, which is over here. 1.7, it says the two objects, so the objects that we were dealing the question, are now brought into contact and they return to their original positions. Calculate the charge after touching. Now, this is an absolute example, ideal example of the law of conservation of charge. We need to understand that the total charge remains the same. So we started with plus 5 nanocoulombs, and we also had minus 15 nanocoulombs. For this particular calculation, you don't have to have the SI units, but we know what they are. We can easily convert. When we add these two together, what's going to happen? We've got more electrons on this side, so this charge is going to try and neutralize that charge. So what we find is the electrons are going to run over there and try and neutralize that, and then these electrons are also going to try and spill over to get away from those electrons, so they'll neutralize each other. The easiest way to show that is to say, what we're going to do is we take those two charges, we add them together, and we divide by 2. So in a sense, the formula is Q1 plus Q2 divided by 2, which will give you the average charge. And that's what's happening. We want to find the new charge, Q nu. And we add the two charges together. Plus 5 plus minus 15 gives us minus 10, divided by 2 gives us minus 5 nanocoulombs. So on each of the charges, there will be now a charge of minus 5 nanocoulombs. So they come together, they attract, they touch, and they repel because the charge has been shared between them. It's spread out over the surface area. Remember, negative charges don't want to live next to negative charges. It's like wanting to live with your mother-in-law. Now, you want to get as far away as possible. Okay, so you want to move away, you want to spread those charges, and that's exactly what happens. You want to move it as far away as possible. So there we go. The two charges will have identical charges now. It will equalize. All will have minus 5 nanocoulombs. So you can write that as minus 5 times 10 to the minus 9 coulombs. Next question, which is also a very interesting one because we didn't touch on it earlier. It says, how many electrons moved from one object to the other while in contact? So let's have a look at it. Let's see what happens over here. To get from plus 5 to minus 5 is a difference of 10. I think you can see that. That's not too difficult. And so we would have a transfer of 10 electrons from this one to this one, and that would leave minus 5 on that side. So we know that there's been a transfer of 10 nanocoulombs, minus 10 nanocoulombs, from the one that was originally minus 15 to the one that was plus 5 nanocoulombs. So there's a transfer of minus 10 nanocoulombs. How many electrons is that? Now, here's the interesting thing. We said conservation of charge is important. It comes from the fact that every atom has the same number of electrons as protons. But a very important experiment found for us that there is an exact unit of charge. There's the smallest unit of charge. We say charge can only come in these packages. We say that charge is quantized. And the charge on an electron is this value. The charge on an electron is 1,6 times 10 to the minus 19 coulombs. So if we want to know how many electrons there are, we've got the total charge that was transferred, we've got the charge on one electron, and every charge has to be an exact multiple of that number. So what we're going to say is the number of electrons, I'm actually going to do it down at the bottom. I'm going to take it down because we've got the information there, 1.8. 1.8, we're going to say the number of electrons is equal to the total charge transferred, divided by the charge on 1 electron. So when we do that, the total charge transferred was -10 nanocoulombs, which was 10 times 10 to the minus 9, divided by 1,6 times 10 to the minus 19. And again, you can use your calculator and you can check that the answer is going to be. Describe the difference in the force before they touched and after they touched. Well, we said before there would be attraction, and after, because they're now both positive, they're both negatively charged, there's going to be repulsion. Okay, last question for this one, or last part of this question, calculate the electric field strength of the +5 nanocoulomb charge at a distance of 10 centimeters. Now, notice here there's no test charge. The 5 nanocoulomb is the mother charge. So when we're dealing with the mother, we must use the equation that doesn't involve the test charge or the force. It's going to be kq, and that's going to be the mother one divided by the r squared. So 9 times 10 to the 9, the charge was the 5 nanocoulomb, 5 times 10 to the minus 9, divided by the distance between them. The distance was a certain number of centimeters, 10 centimeters. We're going to convert centimeters to meters. You divide by 100 or multiply by 10 to the minus 2. So 10 to the minus 2, that's going to give you 1. And so I think you can see that it's not a difficult thing to work that one out. We need to square this, though. So when we do that, we get that all plugged in. Let's put it onto the calculator and see how we go. We're going to go 9 exponent 9 times 5 exponent negative 9 divided by, now 10 times 10 to the minus 2, so that's what we need. I put it in brackets, 10 times 10 minus 2, close brackets, and square it, and we get the answer of 4,500. 4,500 Newton per Coulomb. That's the electric field strength. It's not over though, because what we've got to recognize is that is the electric field strength at that point. The electric field strength is a vector. So we must say it is away from the positive charge because it was a positive charge. So we must say away from the +5 nanocoulomb charge. We've indicated the direction and we've got it all sorted out. Right, question 2, it says an electric field is caused by charge Q minus 15 microcoulombs, charge small q minus 2 microcoulombs is placed at A. So here this is minus 2 microcoulombs, where this one is minus 15 microcoulombs. Okay, so we've got that. It's then this one is moved from A to B, and A and Q are 30 millimeters apart to start with, and you've got the diagram there. It says calculate the electrical potential energy at point A. So the equation we're going to use is the one that says U is equal to K, Q1 or QA, QB over R. Now, again here, you're going to need to make sure that you convert your units, make sure you're using SI units. Okay, let's do this quickly. So as time is short, we'll just quickly do it over here. 9 times 10 to the 9. We're going to then multiply that by Q1, which was minus 15 times 10 to the minus 6. and multiply it by the small one, which was minus 2 times 10 to the minus 6. We recognize this is going to be repulsion. The R value here was 30 millimeters, so we're going to convert it to times 10 to the minus 3 to get into meters. When you substitute that into the calculator, you find that you get a value, and here's the important thing, of 9 joules. Okay, 9 joules. This is a unit of energy, so we're not surprised by that. It turns out to be 9 joules. When we look, remember that was at point A. That was at point A. So what has happened is now we've moved it to point B. We do the same sort of calculation because it asks us to do that, and we're going to substitute in. The only difference here is that we're going to change the value of R. So we substitute 9 times 10 to the 9 times 15 times 10 to the minus 6 times 2 times 10 to the minus 6 over not 30 this time, but at point B is then moved to point B, which is halfway through that position. It's only 15, so it's 15 times 10 to the minus 3. Don't square it in this case. This time, when you substitute into the calculator, you find that you get 18 joules. Okay, notice that the energy has gone from 9 joules to 18 joules. The distance has halved. So it's increased in its electrical potential energy. Now, the next thing we have to say is how much work is done to move Q from A to B. Now, recognize, when it's gone from A to B, what happened to it? It gained potential energy. It went from having only 9 units, it's now got 18. So if we want to find how much work was done, we recognize the work done is equal to the potential energy gained. Then what we can do is simply subtract those two from each other. We're going to say work done from A to B, AB, is going to be equal to the electrical potential energy at A minus the electrical potential energy at B. And when you do that, you get the fact that you've got 9 minus 18, and what that's telling you is that the answer here is negative. The difference is going to be negative 9 joules, and that's because the work was done against the field. It is an external force that's having to push the charge towards. It's not the field doing the work. So there's been a change in potential energy because of the external force. Okay, I hope that makes some sense. Now, calculate the potential difference between A and B. Now, remember the difference between the energy, the work done, and potential difference. Potential difference is measured in volts. V is equal to W over Q. So we need to take the work done, and we're going to need to divide it by the charge that was moved. So in this case, we know that there was negative 9 joules of work that was done against the field, but what was the charge moved? Well, have a look. It was charge A, and that is minus 2 microcoulombs. So it's minus 2 times 10 to the minus 6 microcoulombs. And when you do that, quick calculator will give you the answer here. We're going to say 9 divided by 2 exponent minus 6 equals, and if we put that into scientific notation, it turns out to be 4,5 times 10 to the 6. So in scientific notation, we can do it 4,5 times 10 to the 6 volts. Just show that to you again. If you're not sure how we got that, If you do the calculator there, 4,5 times 10 to the 6, the calculator does it for you, and you've got it right. Okay, so that's the potential difference, because what we've done is we've divided the work done by the charge. Right, let's go and do question 2.5. Read what it says. Calculate the electrical potential of Q at A. Now, if you refer back to the diagram, you will see that Q was that little charge, was the test charge. And what we're wanting to know is the electrical potential of Q at that position. Now, we have worked out, and we know that U is equal to the energy, the electrical energy, which is K Q1 Q2 over R. And we've just been working with that. Now, what we're asked is electrical potential, which is slightly different. What this is known as V, the electrical potential. V is like potential difference, but it's not quite. There is a formula for it. What we do is we say if we want the electrical potential of that, then we know that V is equal to W, which is the energy divided by Q. Now, we can use that energy and divide by the Q value, and you can then see that what you'll get is KQ over R. Okay, so using that formula, we're going to calculate the electrical potential of Q, little q, at A. But notice the Q that we divide by is the Q that is at A. So this Q that's left is the mother charge, is the Q on the mother charge. So we're going to say V at A is equal to K, Q, the big Q, divided by R. And now we're going to do 9 times 10 to the 9. And we're going to then multiply by the charge, big Q, which was 15, it was the big one, times 10 to the minus 6, divided by the distance to A, which in the beginning was 0,3. It's not squared. When you do that and you put it into the calculator, you will find that you get an answer of 4,5. This should be negative. The charge gives you the, this is the one that causes the field. So the potential is negative 4,5 times 10 to the 6. And I hope that you can see that that works out exactly as we've got it there. Let's just check it. 9 exponent 9 times 15 exponent negative 6 divided by 0.3 equals, and there you go. Your answer is 4,5 times 10 to the 6. That's in the engineering notation, and we can put it into the other formats using a calculator. So we've got it right. Remember, this is a unit of volts. This is the unit of volts here. So it's the potential of of Q at A. Similarly, we can do the potential of Q at B. Now, what's going to be different there is you're not going to divide by 0,3, but you're going to divide by 0,15. And if we do exactly that, 9 times 10 to the 9 times 15 times 10 to the minus 6, and you divide by 0,15, you get an answer of minus 9,0 times 10 to the 6 volts. So here we've got the 2. Now, the next question is the interesting one, because it asks us and says, use your answers in 2.5 and 2.6 to confirm the potential difference in question 2.4. And so what we're going to do is just that. What we recognize is we've got the potential at the 2 points, so the potential difference will be VA minus VB, and if you subtract those from each other, this was VA, this one was BB, so I mustn't rewrite it. VA was minus 4 comma 5 times 10 to the 6. And then we're going to subtract minus 9 times 10 to the 6. And if you do that, you get an answer of 4 comma 5 times 10 to the 6 volts, which was exactly what we got over here. Right, let's do the last question, 2.8. It says, if Q has a charge of minus 4 microcoulombs, what effect will it have on the values of the electrical potential energy? So that's U at A. So remember what we've done. We've taken the charge and it was minus 2 microcoulombs and it's now minus 4. We've doubled the charge. So the electrical potential energy, which is K, Q1, Q2 over R squared. What have we done? We know that U is directly proportional to both the product of the charges. So it's not R squared, sorry. It is R. That's not with the force. It's R. But the point that I was trying to get to is it's directly proportional to the charge. So if we double the charge, we have to double the potential energy. So we would say U has doubled. Okay. Now, the electrical potential at B. Well, again, by the same argument, even though it had a different potential at B, this was at A, the U at B will still be double. So U at B is going to be double what it was originally. Next one, and this is the interesting one. What about the electrical potential at A? The electrical potential, remember, we are divided by the charge that was at that position. So if we're dividing by that charge, it doesn't matter. The potential is going to cancel out. So VA is going to remain the same. Remains the same. And similarly, what we would say is the electrical potential, which is VB. Now remember what that is. It's UB divided by the charge, which was Q. Okay, and UB, which would have been the double one, divided by that charge, is going to still be the same. It's going to remain the same. Constant. It's not going to change. Well, that wraps it up. We've done a whole lot of stuff today. Hope that's helped you get a good grounding in electrostatics. Remember, this is important work. You're going to need to know it really well because it could come up in your matric exam. So study hard, go over those problems. If you're not sure of something, practice, practice, practice. Until next time, bye from me. Bye.